just put a delay there, and so that's why I should start that. So, and it's recording from the right channel. Okay, so good. All right, so are there any questions about the homework assignment? Remember I told you guys about the homework assignment that has nested statements in it? So are there any questions about the nested statement homework assignment? Has anyone even tried it? Okay, very good. And any questions? No? Okay, wow. Yep, go ahead.
When it's a nested loop and it finishes, do you just go on to what's right under it, or do you restart the entire loop, or how does that work?
Okay, once you get to the end of the body of a loop, in other words, the last statement, when you're done with the last statement inside a while, then you always have to go back to ask that question again, because you cannot just leave. You have to ask the question and answer false in order to leave the loop.
So once you're in the nested loop, you're stuck there until it tells you to leave it, or?
You have to go back to the first line of the while, and then you reevaluate the condition. If the condition is true, you have to stay in the loop. If the condition is false, then you get out of the loop. Okay, all right. Very good. Well, we will talk about loops again today, but in a slightly different context. So what I'll do is I will show you how pre and post conditions apply to loops as well. Okay, last time we talked about conditional statements already. This time we'll talk about loops. And then what we'll do next will be going back to conditional statements. This time we'll talk about, well, maybe a multi-branch conditional statement. And maybe for the first time we'll see false as the precondition of a line. And then we'll try to look at that and say, well, what does it mean when a statement or a particular line has a precondition of false? Okay, so that's what we'll do today. And we'll also try to formalize, all the steps that we have taken up to this point, so that we don't have to really think that hard when we try to figure out what is the post condition of something. So the first thing I'll do is I'll give you a very simple loop that you cannot trace. So we'll go to a mouse pad. And because we cannot trace it, I don't even bother to use Excel or a spreadsheet to look at the algorithm, because there's no way we can trace it. Okay, here's the algorithm, and then we'll go ahead and analyze the precondition and the post condition of this pseudocode. Line 1 is x get a certain value. Let's say it gets a value of k. And then line 2 is the beginning of a loop. It says while x is less than, let's give it another variable here. Let's say it's q. Okay, while x is less than q, do the following. Line 3 says x gets x plus 1. Line 4 is and while. Okay, that's it. We'll be staring at this algorithm for a little bit of time. Okay, maybe 15 minutes, maybe half an hour. I have no idea how long we're going to be staring at this one. Okay, so what we want to do is we want to figure out what is the precondition and the post condition of all the lines. Okay. Are there any questions about what we are about to do? There's one problem with loops. Okay, with statements or assignment statements, it's pretty easy. You start with a precondition, you do something about it, and then you end up with a post condition. Even conditional statements are pretty easy. The only tricky part about conditional statements is you have two ways to proceed. But if you figure out what is going to happen on one side and what is going to happen on the other side, the conclusion is really just the disjunction of the two. Okay, it is this or that. That's pretty simple. With a loop, it is a little bit more tricky because it is going back to itself. Okay, so it would appear to us that, hey, something cannot possibly be resolved. Okay, so we'll take a look at that. Just like last time, I'll draw a picture, that represents a loop. So this may serve as a review of, a pre-checking loop for your homework assignment as well. But this time, I'm not tracing it. I am just analyzing the pre and post conditions. So here we have Inkscape. And I'm going to draw a picture representing exactly the same pseudocode. Okay. That's pretty easy to draw. This one is a really simple one. The first statement doesn't really do much, so I'm not going to spend too much time to talk about it. It's just an assignment statement. The second statement is a loop. So it's a little bit tricky because it has two ways to proceed. Okay? You can get out of the loop, or you can stay in the loop. So we'll go ahead and, that's not usually how I draw a while loop, but that's okay. It will still work. I just have to make it look kind of funky this time. That doesn't work, does it?
Should open it back up on the top.
Yeah, it has to open up here. I'll just redraw it. Okay. Okay, so that's the first statement. And then with the second statement, it has a way to come back in, and it has a way to exit the loop. So this is my exit branch here. It's going all the way out. And if we don't take that branch, it's going to go continue with a certain statement to execute. And then after we execute that statement, we go back to reevaluate the condition. So this time it's done right. Yep. Okay, there we go. All right. The next thing we want to do is to label, actually put in the pseudocode into the picture. That should not take too long either. Okay, first thing, we will, put the x gets k here. That's a pretty simple statement. And we have x gets x plus 1. And then we have one branch labeled false, because when the condition evaluates to false, we get out of the loop. One branch we label true. When the condition evaluates to true, we have to go through this statement and then go back in again. And we also have to state what the condition is in this case. The condition is x is less than q. That's our condition. All right. So we are almost done. I just want to use some arrows to indicate the direction. Okay, there we go. All right. So here we have a very simple loop with a very simple statement before the loop itself, and we want to figure out the pre and post conditions of every single line of this particular algorithm. Let's start with something that should be fairly simple. Line 1. Okay. The precondition of line 1. We are only interested in x, okay, because in this case, k does not change when we execute the algorithm, and q does not change as we execute the algorithm. So there's nothing really too special about k or q. We don't need to know anything about k or q. X is the only one. But if I make any assumption about x, it's not going to be useful either, because the first thing we do on line 1 is to overwrite the value of x. So we might as well make no assumptions whatsoever in this particular case. So that means the precondition of line 1 is to say, I'm not going to make any assumptions about anything in this case. How do I state that I don't know anything about any variables?
True.
True, exactly. So we have a precondition of true for line 1. And that corresponds to this spot here. So I'm going to label this spot here as our pre1, because pre1 is basically stating whenever we are here, whenever we are about to start the execution of the entire algorithm, the only thing I know is true. That's all. Okay? Which means I know nothing about the variables. And yet, we want to say something at the end of the whole thing. Because if you look at this part here, that is our post 4. Okay? This is our post 4, which is saying when the algorithm exits, when we are done with this entire algorithm, what can we say about x, q, and k? Can I establish any type of relationship between those three, even though I knew nothing about them before the algorithm starts? What do you guys think? Think that might be a little too ambitious?
X is less than Q?
Hmm?
X is less than Q?
X is less than Q. Well, that cannot be.
Because X is no longer in the picture, right? It's
There's no
K.
way.
Well, X is still there. I mean, those three values will still be in the picture.
But didn't K just put the assignment for the X value?
It
the
overwrites the previous value of X, whatever it was.
So you can't run that while statement if K is no longer there as the precondition, right?
Yes, I can. You know, I'm not going to trace it. It will be impossible to trace it, but I can still analyze it.
Okay.
Yep, go ahead.
So, are you asking for what would post 4 be?
Yes,
So-
ultimately we want to derive post 4.
So isn't that just when 2 is false? So therefore it'd be when x, k, and q are all equal?
That is, yeah, but how do you know that it has to be equal?
Well, equal to or greater than?
Equal
Because
to or
it's
greater
not
than
less
Q is 1. Yep. Okay, so you're looking at the code and you're doing a great job analyzing the code and come up with a logical conclusion. But there's a formal way of doing it as well. So we want to take a look at the formal way of looking at it that can be applied to any type of algorithm. Okay? So that's what we are trying to do here. So that analysis is really spot on. All right. Now we want to figure out what is post 1. Okay, so can anyone, without having to use any type of formal derivation, tell me what is post 1? After line 1 executes, we know
X equals K.
X equals K. Okay, X equals K. That's it. Okay, but never put something like this as a post condition. It doesn't make any sense. Because whenever you're stating a precondition or a post condition, it has to be a condition. In other words, it has to be something that can either be true or false. Okay? This cannot be true or false. This is an operation. Okay? This is something that we can do when we execute an algorithm, but by itself, it has no true or false value. On the other hand, anything that looks like this, or less than or greater than, can be true or false. Okay, so make sure that you don't put an assignment operator on the other side, on the right-hand side, when you express a pre or post condition. Okay, that's pretty easy. Well, I'm thinking this can serve as our pre-2. Does that make any sense? Because line 2 is right next to line 1, and nothing should change the flow of the program from line 1 to line 2. So I think we can state that the post condition of line 1 just becomes the precondition of line 2 in this case. Is that working out okay? Okay, from that point on, things get a little bit more complicated. So here we have post 1, which is right here. Let me just label that in the picture as well. So we have post 1 being here, which is also the same as our pre-2. But when you look at line 2, it doesn't make any sense to say anything about post 2. Because when we say post 2, it means, what is the condition after line 2 executes, right? But line 2 is a branch. To proceed from line 2, depending on the condition, we may continue execution on line 3, or we may continue execution at post, which means we are all the way out of the loop. Yep.
How did we get to pre-2 equals post 1?
Because they are sequential.
The thing is, if that loop runs and it comes back with the value of x plus 1, it means that it's no longer equals to k, and therefore the pre is no longer the post. Pre-2 is no longer.
But at this point, it is still the same. Post 1 is basically at this point here, which is before the loop back of the loop itself. Okay, that's a good point. It's a good thing to clarify. So I'm going to use a little circle to indicate, this is pre-1 right at that spot, and this is post 1 and pre-2 right at that spot. Okay. Is that helping a little bit? Okay, excellent. And I can make this fancy too. I can make this slightly transparent. Yeah, no, I'm wasting time. I just could not resist because this way, it doesn't interfere with the picture. It just, show you the spot, but it doesn't cover up the actual path. All right. So, but did I answer your question? Did I address that? Okay. Very good. All right. So now we have to think about what happens after line 2 executes. Sometimes it will proceed to line 3, and other times it will get out of the loop. Okay. Let's just, let's skip it. Okay. Let's skip that, and instead, let's change our focus to this spot right here. In other words, right before line 3 executes, what can we say about the condition? Okay, so this means we are about to execute line 3. The logic of the program is telling me I'm about to execute line 3. The question is, what can I say right at that point, right before I execute line 3?
X is less than Q.
X is less than Q. That's a very good starting point. So let's start with that. Okay, so that would be pre-3, right? The precondition of line 3. So I'm gonna do it on this side here. The precondition of line 3 is, as everybody said, you guys are very good at analyzing this loop here, because in order to get inside the body of the loop, the condition of the loop has to be true. And as a result, X is less than Q must be true. But there's something else too. Something else can also be true at this point.
X can be K less than Q.
Okay, so let's put an and here because because X can be K as well. Not only is it less than Q, it being less than Q is a requirement, right? It has to be less than Q, otherwise we wouldn't be here. But if this is the first iteration, I also know something. I know X equals to K. Are we doing okay so far? Okay, that's not the tricky one. That is really not the tricky one. The tricky one is, but there's something else. There's another way I can end up here. Instead of going from line 1, line 2, and then line 3, there's another way to get back to line 3. It's from line 3 itself, right? I can go from line 3 back to line 2, the condition is true, and then here I am about to execute line 3 again. What does that mean when we are trying to write the precondition of line 3? Post 3 is a component in here. What do you think? It's possible, right?
Pre-3. Okay.
Right? Okay, so if you're having any doubt about this, just bear with me for the time being, because the next one is easy. The next spot or the next focus is right here, right after line 3. What can I say at line 3? I'll just be lazy here. I'll just say post 3. It's just post 3. I don't know exactly what it is, because it looks kind of complicated right now, and I don't want to think about it. Okay? But you can see how post 3, which is the condition that is true at this point, can go back to the beginning of the loop. X is less than Q is still true, and as a result, post 3 becomes a part of pre-3. Can everybody see, how in the loop you can end up with a kind of funny situation where the post condition of a particular line becomes a component of its own pre-condition?
It sounds like time travel.
It sounds like yeah, but it's not a paradox. In program execution, in analyses like this, we cannot have paradox. We cannot have things that cannot be true, right? Okay. So if you want to figure out the answer, the best reference that I can make is Babylon 5. Okay. Okay. So I'm going to point out which part of the storyline of Babylon 5 is applicable to this. Okay. For those of you who watched that show, you know what I'm talking about already. Okay. There's a time loop in that particular TV series. Okay. There's a time loop, and so the story begins, and there's a, I think it's Valen, right? Is the name of the Minbari person, who basically started a revolution and changed the culture of that particular alien planet. And so the timeline keeps going and going and going, and then they had a big, huge war with Earth, okay? And then this guy, Captain Sheridan, okay, a captain got captured, okay? And as it turned out, he got thrown back in time and became that person, became Valen. And that's why, things within that 1,000 years was quote unquote predictable. Okay? It's kind of like that, because the post condition in this case becomes a part of the precondition. Okay? So we'll just let it stick like this, okay? And then we'll continue to state what is post for. Okay, post for is down here. I'm going to change our focus here and say, okay, last we'll put our focus here. What is post for? Okay, now post for is kind of easy to figure out because the first thing we notice is there's only one way to get to post for. Q is less than Q, X is less than Q has to be false. Okay, so that's one thing that we know for sure. Is that okay? Mm-hmm. Okay, so we'll say, post for is, it is not the case that X is less than Q. That part we know for sure. But there are other things that we also know. Because if we go through this conditional part and skip this part altogether, then post 1 or pre 2 also has to be true. Because we just go through this statement here. At this point, I just skip everything and then exit, because X is already not less than Q to begin with. Okay, so we have X equals to K again, appearing here. But there's another way to get to it, because it is possible that we go through this several iterations, at least one. So we have post 3 here. Post 3 is true all the time here. Getting back to here, post 3 is still true. But even though post 3 is true, X is less than Q is false, then that basically makes us take this alternative path and get to post 4. So that means inside post 4, we also have a component of post 3. Okay, so far, I can write all this down because of just the analysis of the flow of the logic. Okay, are we still doing okay so far with what we have at this point? It is far from being resolved, but we can at least state how the pre and the post conditions relate to each other. Any questions about this at this point? No questions? Okay. All right. So if there are no questions about this, you can recognize post 3 to be one thing that seems to be everywhere. Post 3 seems to be a part of pre 3. Post 3 obviously is itself, and it is even in the exit condition. Okay, after you get out of the loop. And that's why it has a very special name. It is called a loop invariant, because this is the one thing that does not change as you go through a loop. Okay? While you are in a loop, it is true, but even when you exit from a loop, it is still true. Okay. So let me just kind of write down here. Post 3 is known as the loop invariant. Okay. But what exactly is it? I mean, can we figure out what post 3 really is in this case? What do you think?
To throw something out, is it a X is greater than K?
No, it's not. Now, but if you have a suspicion, there's a way to test whether it works or not, right? Because you can just plug it in and see whether it makes sense or not. Okay? So I'm just gonna take a stab at this, okay? So without telling you guys why I have this suspicion, I'm just gonna say, tech suspects post 3 is X is less than or equal to Q. Okay? Not just less than, but it's less than or equal to. I don't know whether it's going to work out or not. I'm just going to have to plug it in and see whether it leads to any type of contradiction. Because if it leads to any type of contradiction, I know this assumption cannot be true. Okay. Okay, so based on this suspicion, we can now restate pre 3, right? Pre 3 is X is less than Q, and x equals to k, or x is less than or equal to q, and that's what we have. Is that okay so far? Because I made this suspicion, so that means when I rewrite pre-3, I can take away post-3 and instead substitute it with x is less than or equal to q. Are we doing okay so far with this?
Yeah, so you're kind of saying like these are all of the different options that can be when you hit pre-3.
Yes. Right before I execute line 3, this has to be true if my suspicion is right.
So, and just so I can kind of understand the logic, is this a good practice to do? Just to kind of say, hey, when I'm writing out this algorithm, here are all of the possible results of running this particular.
It's good to analyze your algorithm and be able to at least understand. Okay, based on what we know, based on just looking at the algorithm, I can come up with this analysis. Okay. Instead of running the algorithm to find out what it's going to do, it's nice to be able to state what the conditions are at a certain point. Okay. And I just remember I gave you guys a brain teaser, and I have not addressed the brain teaser about the maximum thing. So we'll go back to that one. You guys have to remind me to do it. I'm going to pass the row sheet. We are about 25 minutes into the class. I think it's fair to pass the row sheet at this point. Yep.
Oh yeah, that can't be right because if it's equal to q, then it's false on the.
But it's less than or equal to.
Well, if it's equal to, it would be false, wouldn't it? So wouldn't
Look,
it be?
wait. Okay, it's less than or equal to, which means it doesn't have to be equal to. Okay.
Oh, okay,
It will all work out.
Yeah,
Okay?
I see why.
It's gonna all work out. I'll show you guys why it's gonna all work out. Yep.
So we don't do
Pre-4. Yes, we don't state anything about pre-4 because line 4 is the end marker of a loop. So pre-4 is kind of ambiguous because at the end of the loop we are supposed to go back to the beginning. So we are not gonna say anything about pre-4. Okay, so getting back to this one here, I'm gonna have to do some manipulation and say, this looks kind of funky to me. I don't know exactly how to interpret this. Okay, so let's go ahead and figure out how we can interpret this. Do you guys still remember what is the distributive law in regular algebra? Okay, distributive law is an axiom in regular algebra. It says, A times, in parentheses, B plus C is the same as A times B plus A times C plus B times C. Okay, so I'm going to write it out here. Okay, so distributive law is saying in regular algebra says, A times B plus C is the same as A times B plus A times C. Okay, A times B plus A times C. Okay. I'm better at writing than to spell it out. Okay, but is that okay so far? Okay. Everybody is saying, okay, yeah, we know about that one. Well, as it turns out, it's true in Boolean algebra as well. Okay, if you change multiplication to conjunction, then you change addition to disjunction, it works out the same way. Well, whenever I claim anything like that, you want to say, I don't trust you, Tag. Prove it. Okay? Because I do make mistakes. Okay? This is a good time, since this class is a little bit ahead of the other class, so this is a good time to go for another digression to kind of say why it is important to prove what seems to be simple and intuitive. When I was working on my dissertation, which is really just a long paper, mine was actually a long proof in math, even though it's a computer science degree. At one point, actually at the very beginning of my dissertation writing process, my advisor told me and say, Tag, you're going to continue to work on this thing here. A portion of that was already done by somebody else's, master's degree, a master's thesis, which is a shorter paper, but it's, on the same topic. And, my advisor said, okay, you can just you can assume something is already done, and you just have to kind of extend it, continue to work on it. And that was a theorem, okay? That was a theorem which is basically a statement that is believed to be true, or usually it is proven to be true, okay? So, and I was working on my dissertation based on that particular theorem until at one point, it's just a gut feeling that this is not necessarily true. I'm not 100% sure. I just have a gut feeling that this may not be true, okay? Maybe sometimes it is not true. So I went to my advisor and asked him, are we sure this theorem is true? And he said, yeah, it was proven, in the other master's thesis, it's already proven. And I go, okay, I'll check it out. Okay, I'll just kind of read the proof and convince myself this is nothing. There's no harm here, no danger. So I read the master's thesis, and at that point it just says, obviously, blah 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 blah, has to be true. Okay, so there's no actual step-by-step rigid proof that the theorem was true. Okay, it was just obvious, but it wasn't obvious to me. Okay, maybe I'm just slow. Okay, but it wasn't obvious to me. So I told my advisor, I don't know. I mean, I cannot find the actual hard proof that this is actually true. And then my advisor said, oh, don't waste your time. Just keep working on your own stuff, right? I couldn't stand it. So I spent 1 week to think about this and try to come up with a counterexample, and I did. Okay, when you try to prove something right, no matter how many times you prove it to be true, no matter how many cases you throw at it to say it is true for these and for this case, that's not a good proof that it is true. But when you want to prove something is wrong, you just need one case. Okay, it's called a counterexample. Okay, a counterexample is all that you need to prove something is wrong. Okay, so it's easy to prove something wrong than to prove something is right, in a sense. So I came up with that counterexample, and I went back to my advisor and presented the counterexample. Did I make a mistake here, in the counterexample? No, I did not. Yeah. Okay, and my advisor, all he said was, "Oh, that was it. That was it." They didn't do a single thing because the committee of my dissertation had exactly the same professors as the committee for that particular master's thesis. So I cannot just stir this thing up and say, okay, who reviewed this particular master's thesis and let this be published. So I wouldn't stir it up. But I did went back to the lab and talked to my lab mate. There's another guy in the lab whose work is based on the same theorem. And I said, oh, you know what, that theorem is false. I mean, it's not true. Oh, he just went ballistic because he was on his master's degree. And it took him almost 3 years already, so it's behind schedule. And now, basically I'm saying, well, you know what, those 3 years are mostly wasted. So he wasn't happy about it. But that's, it's just an example to show you why it is important not to trust somebody's claim and say, yeah, it seems kind of obvious, we'll just take it for granted. Instead, you want to get the actual proof, okay? Just look for the proof, and the more you do it, the more you will be proficient at, arriving at your own proof, doing your own steps to prove something is correct. So let's go ahead and prove this one, okay? So we want to prove this. This is what we want to prove. We want to say, A and B or C is the same as A and B or A and C. Okay. In other words, I'm just using and in place of multiplication. I'm using or in place of addition. Okay. I mean, this is not obvious. This really is not obvious. So if it's not obvious, we have to prove it. But how do we prove something like this? Well, as it turns out, there's an easy way to do it. Only because this is Boolean. Okay. So this is a table right now. I'm not using a spreadsheet, but I'm simulating this is a table. We have 3 independent Boolean variables. In other words, A is Boolean. It can either be true or false. B can either be true or false. And C can either be true or false. But they are independent. So that means when A is true, B can be true or false, C can be true or false. A does not determine the other two, and vice versa. Okay? So how many combinations can I get? Okay, A can be true or false. Okay, so it can be true, false, true, false, true, false. B can be true while A is true, but B can be false while A is false too. And the same thing applies to C. So how many combinations can I get? Unique combinations.
9.
9 is one too many. Exactly 8. Because 2 to the power of 3 is 8. Okay? Each independent variable has 2 choices, but since they are independent, we end up with 2 times 2 times 2. That's the number of combinations. And I'll enumerate everything. While A is true, okay, A can be true, B can be false. Can be true or false, right? B can be true or false. While A is true, B is true, C can be true, but C can be false too, because remember, these variables are independent. So the same thing applies when A is true and B is false. C can be true or false. Also, I think you guys are seeing the pattern, right? So being kind of lazy, I'm going to just do a copy and paste and replace these with false. Okay, that's all. You cannot do something like this for regular algebra because you cannot enumerate all possible cases for numbers. But when we are dealing with Boolean values, we can easily enumerate all possible cases. And that makes proving something like this just kind of tedious, but it's not really difficult. Are we doing okay so far with this part?
Just on the programming side,
Right.
the only reason why this works is because the equal operator is it's not counting this as its own variable, but rather running the argument against each
This is a
individual
question.
variable.
I'm asking, are they the same? We don't know yet. Okay, we
Right,
want to
but
prove that they are the same.
A and B or C is not its own variable. You're not running it like
It is an expression. It is.
expression, just each individual. Okay.
Yeah, it is an expression just like A times B plus C is an expression.
Okay.
But in this case, it's a Boolean expression, so the entire expression has to evaluate to either true or false. Okay? Okay, so let's see how well you guys know your Boolean operations. Okay, so this entire thing, what should it be when A is true, B is true, and C is true? The whole thing has to be true. Okay, very good. What if C itself is false? It is true because B or C is still true. A is true, so we have true and true. What about this one? This is just the flip side of the. So this one is true. What about this one? False. This one is false because B is false, C is false. False or false is false. And then we have A being true, so we have false. We have true and false, which is by definition false. Okay. All of these are false because if A is false, forget it. The whole thing cannot be true, right? So I can just say that these are all false. There we go. All right. So now we move on to the last column and try to figure out what about this expression? What is this expression going to result? When I have A being true, B, C being true, and C being true. The whole thing is going to be true. Okay. What if C by itself is false? It will still be true because A and B is still true, and this is a disjunction. I only need one side to be true for the whole thing to be true. What about this one, when B is the only one that is false? This will still be true because A and B is false, but A and B is false, but A and C is true. We have false or true, so the whole thing is true. What about this one? It will be false because both sides of the disjunction will be false. And what about this one? It will be false because this conjunction, which has A, will be false. This conjunction, which also has A, will be false. And you can apply the same reasoning to the rest of the cases. Okay. All right. Okay. So where's my proof that the two expressions are the same? You look at the two columns.
They're both the same.
They're exactly the same, right? There's no one row is off, So now I have just proven A and in parentheses B or C is in fact the same thing as A and B in parentheses or A and C in parentheses. Okay? This is a very useful, powerful technique to prove theorems involving Boolean operations, because you can enumerate all the possible cases. If you find one row to be different, then they cannot be the same. But if all the rows match, then you know that they are equivalent. They will result in the same value when you evaluate the expression.
Like an array or something? Like in an array or something? Not
No.
necessarily?
No. Has nothing to do with arrays.
No, just okay.
Yep, go ahead.
What's the mathematical way to prove it?
I do not know of any mathematical way to prove it. Yep. All right. So now that we know this, we'll go back and apply the distributive law to that particular expression. So we'll end up with okay, that's the general pattern. And I'm going to copy this one and paste it, and paste it here. Copy this one and paste it here. Copy this one and paste it here. Okay, so the second step is really just the application of the distributive law to the first line. And by the way, I'm not going to test you guys on this sort of thing. This is not a Boolean algebra class, but I do want to give you the exposure of this kind of stuff because some of you will find this useful in your other classes. Okay. All right. Attack, that doesn't seem to help us. I mean, it just makes it even worse. I mean, look at this. I turned something that is simpler with 3 items into something that's even more complicated with 4 items. What is this buying me? It's not buying me anything. Okay, what do you think? What do you think is buying you? Yep.
I think it's getting you back to inferior to Q.
All right. So let's focus on the one side instead of both sides. Let's focus on this guy first. X is less than Q and X is less than or equal to Q. Is there a way to simplify this? Okay, think about the number line. Okay, so let's say X and Q are integers. Okay, so make it very simple. So we can easily just put dots on the line. Okay. So in drawing this, it's not going to be captured, by the screen, but it's okay. So let's say, X is here. This is our X here. Okay, actually that's not the way to put it. This is our Q, and this is our Q minus 1. Okay. When we say X is less than Q, which part of the number line can X be? Okay, right here, right? From here and on. That represents, X being less than Q when both are integers. Is that making any sense? When I say X is less than or equal to Q, then on the number line, I'm starting here instead. So this is saying X is less than or equal to Q, right? Sorry?
And the whole thing is just X is less than or equal to Q?
No, but I'm using conjunction. So when you have a conjunction, that means both expressions have to be true at the same time. Now, if both expressions have to be true, X is less than Q has to be true, X is less than or equal to Q has to be true, that means the equal to Q part cannot be true. So that means I can actually simplify that expression, the one that is highlighted at this point, to the following. I can just simplify this whole thing to X is less than Q. Is that okay? Yeah. The other part I cannot simplify because there's just no way for me to tell whether X equals to K. Well, actually I can tell here as well. Okay. So now we'll focus on the other side here. Okay. We'll focus on this side and say, can we simplify that too? Now, if x is less than q is true. Now, remember, the entire conjunction can be true only if both sides are true at the same time. Okay? So we are looking at a situation where x is less than q and x equals to k. Can I simplify this? Is there an easier way to say that? Okay, let's think about it. So once again, I should not have erased the entire number line, but that's okay. All right, so we have q here. We have q minus 1 here. And because x has to be less than q, right? Because otherwise, this won't work out. So x has to be, k has to be less than q. So k is somewhere here. I don't know where, but it is somewhere around here. Because both expressions have to be true.
That x plus k is less than q?
No, that's not how. It's easier. This is a very easy way to. That's an easy way to simplify it. Because when we say that x is less than q, we are saying, oh, all of these points can be x. When we say x equals to k, we mean this point, only this point can be x. What is the intersection?
K equals Q.
K equals
X equals k is the intersection. Okay, that's the only spot where both expressions can be true at the same time. Is that making any sense?
Because you're saying the precondition where k took the x assignment, then no matter what, both of them have to be greater than q because it's kind of like because the assignment, or I don't know, just trying to play this out.
No, it's the intersection because when you say x is less than q, you have a bunch of values that can make it true. Okay, a bunch of values of x that can make it true. When you say x equals k, there's only one place on the number line that can make it true. X has to be k, right? If both are true, because the conjunction itself it has to be true, right? So if both are true, then the only thing you can make a conclusion and say x has to be k. No, it's not.
It's not clicking. I don't know. Sorry.
Okay. Let me think of another way to explain it.
I think that's
Huh?
if you get the number line, that's really how you can best understand the whole.
I'm thinking of some analogy that is completely unrelated to numbers, but yet still has the same element.
We can break it down the same way as we did on the bottom, like x inferior to q, or x inferior to q, and x equals k, or x inferior to q. And the first one will eliminate because both sides are the same, and that will take us back to x equals k or x inferior to q. Like the line just before the one you just typed.
You mean this line here?
Yeah. We'll break it down the same way we did on the bottom.
But you cannot. Well, you mean you use the distributive law on it again?
Yeah.
Then you have x less than q. You still end up with the same situation then. You still end up with a combination of x equals k and x is less than q. You still end up with the same combination.
It'll be or. It won't be and because the parentheses are surrounding the end.
It'll be an or. So you would basically end up with this situation.
Exactly.
Yep. Okay, that's one way to do it. But it does make sense, if x is less than q is true, x equals to k is true, we can simplify the whole thing to x equals to k. How many people have exposure to set theory in high school or no? They don't teach set theory in high school about unions and intersections. No.
Maybe under a different name.
No, it's can't remember the name of this diagram. So you have set A, set B. This is the intersection, and then the whole thing is the union. Venn diagram. Okay. So do you guys talk? Do they? Okay, you have this exposure, right? Okay. So in this case, we have a very special case because we have one set being, kind of big, and the other set is right here as a single dot. and I'm looking for the intersection. What is the intersection here? That one dot, right? That's why the expression. That's why this expression here is simplified to a single point. All right. But the next line is going to go in the opposite direction because now we're looking at the union of exactly the two things. When you look at a union, then it becomes the larger thing, the thing that is containing the whole thing. That will become the result. So we end up with just x is less than q. Everything else just disappeared. Okay. Any?
Oh, okay, it's an or.
Because it's an or, so you take the inclusive one. Now they do have to overlap. Okay, one has to completely cover the other one in order to make this simplification. But you take the bigger one when you're performing a disjunction. You take the smaller one when you're taking a conjunction. Okay. So was I right about crazy math? Like in the previous class? Not quite yet. Okay, we're getting there.
It's bigger when it's a conjunction, is that what you said? It's the bigger option when it's
Disjunction.
When it's disjunction?
Yeah, when it's a disjunction, you take the bigger one. When it's conjunction, you take the smaller one. But the prerequisite is that one has to completely contain the other one. Okay, so that's our pre-3. Okay, now getting back to the original program. How far did we go? Not very far. So what we want to do now is to say, knowing this is what is pre-3, what is our post-3? Now, you guys already know the answer, right? Okay, knowing pre-3 is x is less than q, and line 3 is just adding 1 to x. The fact that it is inside a loop is irrelevant, because all we are doing is, oh, this is pre-3, this is line 3, what is post-3? If it is in the loop, doesn't matter. If it is not in the loop, doesn't matter either. Okay? So if I know that x is less than q before I add 1 to it, what can I say after I add 1 to x?
Same thing, right?
Okay, the first thing I can say is this, okay, which looks awfully confusing, right? Because we have an add 1 in line 3. How come I have a subtract 1 here? Because the subtract 1 let me undo the effect of the assignment statement. So whatever was true before is still true. I'm just undoing the effect of line 3. Okay? But that's not what I claim. I mean, it's not the same thing as this. I mean, this is definitely not like that. Or is it? If I tell you that x and q are both integers, do you think those two expressions are the same? When I say x is less than or equal to q, both being integers, is that really saying the same thing as x minus 1 is less than q? Or x is less than q plus 1? They're saying the same thing. Okay? So that's how I can make that connection and say, oh, you know what? I can say that this is actually just x is less than or equal to q. And guess what? I have just proven myself right. Because I plugged in what I think is post-3 into pre-3, and I ended up with a consistent result out of pre-3 and also out of post-3. Everything just works out. Are we doing okay so far? Okay. Okay, so knowing, now we have just confirmed that post-3 is in fact x is less than or equal to q. Can we get to post-4 now? I mean, post-4 is this part here. Okay, so what can we say about post-4? So let's try to plug it into post-4. So I'm going to repeat post-4, especially the part that does not involve post-3. The part that does involve post-3, I'll substitute it with the post-3 that I know it is. Okay? So now our expression becomes this. I'm going to roll this up a little bit so that people in the back can actually see it. Okay. So now I want to simplify this. Okay? It's time to simplify this whole thing now. The first thing I would do is to change not x is less than q to x is greater than or equal to q. Is that okay? I mean, does everybody understand or see why the negation of x is less than q is x is greater than or equal to q? That has nothing to do with whether they're integers or not. It applies when, to all the values of x and q. And then the other part is the same. I'm just going to copy that. Oops. There we go. Okay. And what I'll do is I'm going to apply the distributive rule again, okay? Because we have the and on the outside, the or in the inside. It fits the pattern earlier, so we can apply the distributive law again. And by the way, in Boolean algebra, you can apply the distributive law even when it's reversed. You have a disjunction on the outside and a conjunction in the inside. You can actually apply the distributive law, but you have to change the operators. Okay, but I'm not dealing with that right now, so I'm not going to put too much time into it. Okay, so we're going to do this part here. So we'll have a something and something, or something and something here. This is the one that is going to be common in both. And then this one is going to be appearing on the left-hand side, and this is going to be the one on the right-hand side. Okay, so that's what we have at this point. Now we look at this mess here and go, can we simplify this? I mean, is there a way to look at this in a way that makes sense? I mean, can we simplify this? Okay, let's take a look at the first one and see whether we can do something about it. X is greater than or equal to q, and x equals to k. How do I simplify this? Both are true. It's a conjunction, so we take the smaller of the two. X equals k. Very good. So we will simplify this side to x equals k. Okay. What about the other side? Wow, this looks kind of messy to me because it looks like it's a contradiction. It cannot happen. I mean, x is greater than or equal to q, and x is less than or equal to q. Can it happen? Yes, that's exactly one point where the two sides overlap. When x equals q. Okay, so this entire thing, simplifies to x equals q. Now, if you want to prove that x is greater than or equal to q and x is less than or equal to q, it's just x equals to q, you can actually use the distributive law to prove that. But it's going to be a big, huge mess, but you can do it. Does anyone want to see the approach? Okay, maybe later. Okay, let's finish this first, and then later on we'll go back and do that part. Okay. Okay, and there's no way to simplify this anymore. In other words, x equals k or x equals to q is the answer. The reason why x equals k is still here is because if you look at this algorithm here, what if k is greater than q greater than q to begin with? Then you won't even go through one iteration, so it will just remain as the value. Okay, so that's why Now, on the other hand, if you make the assumption that k is less than or equal to q, then you can simplify it one more step and just arrive to the conclusion that x has to equal to q itself.
It can't get above it. Because it can't get higher than q.
Correct. Okay, so getting back to that mess here. Okay, the question is, if I claim x is greater than or equal to q, and x is less than or equal to q, how can I establish the equality or the equivalence to x equals q? That was the question. Okay. When we say x is greater than or equal to q, I'm hiding a disjunction in it, right? Because it is the same thing as saying x is greater than q or x equals q. Okay? This expression is actually hiding a conjunction inside. So that means the other one is about the same thing. We are hiding a disjunction in the inside too. So we have, but this time we have x less than q or x equals q. Okay? So what you do is you apply the distributive law twice. Okay? In other words, you do the cross product of the two. So you end up with x is greater than q and x is less than q as one component. You have x is greater than q. Let's see here. Yeah, you have the cross product of the 4, and what you will see as the remaining part is x equals q, and x equals q is the only one that can be true, and that's the only thing left. And that's the proof of it. I mean, I'll leave the rest to you, to prove it, but that's the approach of proving x equals q is the answer. But it makes perfect sense intuitively as well. Because you look at the number line, one is including q on this side, the other one is including q on the other side. The only intersection is q itself. So that's the other way to look at it. All right. Are we doing okay so far with analyzing loops? You okay? Okay, so about the brain teaser. Okay, so we have to go back to the previous lecture. And I have the advantage of having YouTube, so I can just kind of flip to the right, moment of the previous lecture. The funny thing is I can actually replay this lecture even when it's being recorded. Which will look kind of interesting when you watch it. Yeah, it okay, but right now I'm just going to go to YouTube, so we can just refer to that one. Welcome to YouTube. And close this.
Ad blocking.
It doesn't show up.
I think it'll be another layout change.
Yeah, that's, YouTube. Okay, so go to my videos, and it's the PM class. Close to the end. There we go. Right there. And just a little more. There we go. Okay, I'm gonna pause it here and then just type it out. Okay, I know you guys cannot see it because it's really small. No, stop. Okay, x is greater than y and z equals to x, or x is less than or equal to y and z equals to y. Okay, so that's the post condition of the logic that we have already described to find the maximum of 2 and then put the maximum into z. That's the conclusion. That's the post condition of the whole thing. But is that really saying that z is the maximum? That is the question. Okay? So I'm going to roll this off the screen for now, because what I want is to have you guys to think of how would you express that z is the maximum of x and y. How would you use and or not greater than, less than, or equal to in order to say that z is the maximum of x and y? Okay, so we'll go for some usual approach to do this. So we'll say, oh, z is the maximum of x and y means the following. It means z is greater than or equal to x, and z is greater than or equal to y. But that really is not the definition. I can give you one quick example that z may not be the maximum. Let's say x is 5 and y is 7. Okay, 5 and 7. I can make z 20, right? 20 is greater than or equal to x, and 20 is greater than or equal to 7, but 20 is not the maximum of the two. What am I missing here? What I'm missing is the maximum has to be the same as at least one of the two. Am I making any sense here? So this is a good starting point. It's a good starting point to claim, to state that z is the maximum of x and y, but it is not restrictive enough. What I really need is another conjunction to further restrict the value of z and say that z has to equal to x or z has to equal to y. In other words, if all three conditions, this condition, and also this disjunction, if all three are true at the same time, then z is the maximum of x and y. Are we doing okay so far with this? Okay. So now the question is, going back to our conclusion from the last class, which is this part here, can I look at this and come to the conclusion and say, oh, it's really saying the same thing as that? That really is the question. Can I derive one from the other? Because these two should be equivalent when I claim the algorithm is correct. So I should be able to derive one from the other one. Okay, what do you think is what do we need to do? I think we need the distributive rule, but this time it's applied in the reverse of the operators. Okay, let me explain what I mean by that. Now, in arithmetic, it only applies one way. In other words, you can only use the distributive law when you have a times, in parentheses, b plus c, then it becomes ab plus ac. The multiplication is implied. That works for arithmetics, right? Algebra classes, that works. But the other way does not work. In other words, when you have a plus b times c, you cannot, okay, this is not equal to, you cannot claim that, a plus b times a plus c. These two sides are not the same in normal arithmetics, right? Okay. But in Boolean algebra, it actually works the other way as well, okay? But in Boolean algebra, it works both ways. So you can have a or b and c is actually equivalent to the following. It's equivalent to a or b and a or c in Boolean algebra. And every time I make claims like this, you will say, "Tag, prove it." Right? Okay, so we have to prove it. We'll use exactly the same technique as last time. We end up with 8 rows because each row represents a unique combination of the values in the variables a, b, and c. They are independent. So we have b being true, true, false, false, true, true, false, false. And then we have true, false in the last column. Oops. I said one thing and did something else. False. Okay, there we go. When everything is true, obviously the entire expression has to be true. When c is false, the whole thing is still true. In fact, whenever a is true, I can say the entire thing is true because the outer operation is a disjunction. If at least one side is true, which is a, then the whole thing is true. So I can claim this whole thing has to be true regardless. Now, when I look at the other 4 rows, when a is false, then b and c both have to be true in order for the whole thing to be true. So this is the only case when the entire expression can be true, because b and c means both b and c must be true for the entire disjunction to be true. And I need it to be true because the other side of the disjunction is false already. So for all the other cases, we have false here. This actually looks like an inversion of the other table. The other table has 3 true cases, and then the rest are false, and then this one is the reverse. We have 5 true and 3 false. Okay, let's look at this side here, because I need that side to be exactly the same in order to say that the expression is, the 2 expressions are equivalent. Okay, a or b, they are all true, so the whole thing has to be true. This one is trivial. All right. Now, the first 4 cases are actually trivial, but you might want to just go through the basic operations just to be sure. But I think they are all trivial because if you look at both disjunctions, they both contain A as a component. But A is true for the first 4 rows, right? And for any disjunction, only one side has to be true for the entire thing to be true. So since A is already true, the disjunction, both disjunctions must be true. If both sides of a conjunction is true, then the conjunction itself has to be true. So the first 4 cases can be reasoned out like that, but you can always just evaluate the disjunction, and then the conjunction to be absolutely sure that the answer is true. This one is true as well because A is false at this point, but B is true, so the entire disjunction on this side is true. A is false, but C is true, so the entire disjunction is also true. Then we have true and true, which means this entire thing is true. The question now is, are these false? The last 3 cases, are they false? Okay, let's take a look at this one. I'm going to go slow this time. We have A being false, B being true, so this whole thing is true. So that looks kind of promising. A is false, C is also false in this case. False or false is false. So this side is false. We have true and false. The end result is false. Okay. So if you go step by step, you will also see that all remaining rows will also match. So that is my proof that distributive law applies the other way around when you have disjunction on the outside and conjunction on the inside, and it still works. Okay. So knowing this, what we'll do is we'll go ahead and just expand the entire thing. We'll look at this thing here and expand the entire thing. Now you don't have to. If you want to expand the entire thing, you can do it step by step, or you can just do it all in one. I'll just go ahead and do it, step by step. So if I apply that distributive law, then we end up with. I'm going to keep this side basically the same and only expand on the other side. Then we have something and something. This one has something or something, or something here. And I said we'll keep this whole thing intact. So we'll copy and paste it. Paste it here, and this one will be this side, and this one is going to be on the other side. Okay. Is that working out okay so far? Well, first of all, let's take a look and make sure that I did not make any stupid mistakes. Okay, or on the outside and in the inside. I'm only focusing on this and here and in the inside. And the result is or in the inside and on the outside or in the inside. Okay. A in this case is this entire expression, which is this entire expression here, which is also this entire expression here. B is this expression, which goes, oops, I take it back. B is this expression here, it goes here, okay? And then C is this expression, it goes here. What would be my next step if I were to expand the entire thing? The next thing I can expand is the distributive law applied again, but this time, to each one of the inside. So we have basically we end up with a cross product. So we can expand this, and then we can expand that. I think that's going to take a while. Maybe I'll just do this, and the next class I'll show you all the steps, instead of going through this all in the class. I'll save you some time. Okay? You guys are going like, okay, maybe we can skip this. Well, we're not going to skip it. I'll just give you the answer next time. Okay? Step by step, to prove it. Are there any questions at this point? Now, so far we have reasoned out stuff just by looking at things and looking at the flow of the logic, but things are still not very mechanical. I like things to be mechanical. In other words, I look at an expression or I look at an assignment statement. I'm going to apply some rules. Okay, I will check whether it fits a certain condition. If it fits a certain condition, I will apply a certain rule, and that will get me the post condition. In other words, I want everything to be mechanical. I don't want to have to go through all this random proof stuff every single time. So that's what we're going to do next. Is I will get started today, and then we'll continue with this next Tuesday. Okay. So what I want to do is to show you an example here. I'll just say this is line 65. And on line 65, we have something kind of interesting. Instead of telling you exactly what is on the right-hand side, I'm saying I'm only going to say that it is a function that depends on x. How many people are somewhat familiar with the concept of a function? Okay, very good. So I'm just saying that the right-hand side is some kind of a function. I don't even tell you what it is. Okay. And as a precondition, I will tell you, okay, this time I'll make it a little bit more concrete. I'll just say that x is, I don't know. I'll just say that x is less than k. Okay. That's all I'm going to tell you. I'm not going to tell you what k is either. I'm not going to tell you what x is either. And I'm asking you, can you tell me what is the post condition of line 65? Well, that seems kind of, that's a tall order, not knowing what f is, not knowing what function f is. Okay, I'll throw you a bone. Okay, I'll throw you one bone, and that will change everything. Okay, because what I'm going to tell you is there exists f. This prime here is actually the negative one superscript, which means the inverse, as an inverse function of f. Okay. Now, what is an inverse function? Think of it as undo, right? If a function is do, then the inverse function is undo. You get back the original item. So by definition, if f prime is an inverse function, then if you apply f prime to f of x, you get x back. If you apply f to f prime of x, you also get x back. That is the definition of an inverse function. And it is true for all possible values of x. Okay? You cannot just say, oh, it applies to certain values of x. No, it has to apply to all values of x in order for f prime to be classified as an inverse function. That is awfully abstract here. Can you give me an example? Okay. Well, if f of x is defined, I'm just going to give it a very simple definition. It's x plus 1. What do you think is the inverse function of x plus 1? X minus 1. Okay, that's a good suspicion. Now prove it. Prove that x minus 1 is the inverse function of x plus 1. Can we do it? Yeah. Absolutely, because what we'll do is we'll say, okay, well, let's apply f prime to f of x. Okay, so I'll just do it one level at a time. I'll keep the f prime on the outside, but in the inside, I would say, oh, f of x is the same as, guess what? It's the same as x plus 1. Is that okay? Now I have to apply f prime to the whole thing, x plus 1. What is f prime doing? F prime is basically subtracting 1 from whatever is in the parentheses of the f prime. So it becomes x plus 1, the whole thing, minus 1. Okay? What is the answer? It just becomes x, right? And which rule in algebra do you use to establish that? It has to do with order of operation? Associative law. Yep, because you can change the order of operation. All right, so that's good. I mean, this is proof that, if I define f of x to be x plus 1, then f prime of x, or the inverse function, is x minus 1. Now, I know some of you are taking calculus or differential equations, and the prime means derivative. So in this class, I'm just using it as the inverse function because I can't do the superscript minus 1 easily with a text editor. Okay, so just keep that in mind and don't get confused with your other classes. Okay, and we got 10 seconds left. So what I'll do is I'm going to shortcut this whole thing and say that post 65 is this. F prime, the inverse function applied to x, is less than k. As a post condition of line 65. And it applies to any function f. As long as there's an inverse function, that will be true. Makes sense, because if I can undo an operation, I can reverse my way back to the relationship between x and k prior to the assignment statement. That's the whole rationale of this. Okay, but it's going to come in handy. We'll talk about this next Tuesday. So have a nice weekend, but don't forget to kind of read ahead of me a little bit and do the homework assignment. That's my